So organized counting. So this is going to be, it's kind of a test. So just like all the tests that I've created, I'll put the link to the test if you want to try it on your own in the show notes below, so you can download it. And what I'm going to do is I'm going to go and walk through every single question, solve the questions so you can come back and then check your solutions if you like. So we'll do them kind of one by one. Okay, so let's do it. So question number 1. So I'm going to just copy it down. So in question 1, so this test is all about counting, and it relates back to, in this case, just putting an order on 6 people with regards to giving a presentation. So question part 1A, how many ways can the order of presentations be set? Well, if you have 6 people, so order certainly does matter. So you would have, so let's say 1, 2, 3, 4, 5, and 6. And now in order to be rearranging this, you may remember, okay, so if you have 6 people, so in the first spot, okay, you have 6 choices basically to pick from. And then you have 5 remaining people, so you have 5 remaining choices. In the second spot, 4 remaining choices, 3 remaining choices, 2 remaining choices, and then only 1 at the end. And if you want to know how many different orders there are, well, we use the multiplicative kind of principle or property, so we're going to be multiplying these through. So we would have this, and as you know, so this is nothing else but simply 6 factorial. So we can get that answer, okay, to this, okay, by applying it through, so 6 factorial, or just doing it directly, so that would have been 720. So there are 720 different ways that you can order 6 individuals to give a presentation, which is pretty crazy, but that's what it is. So that's part A. Now it gets a little bit different as we continue on with these different parts. So part B, how many ways can the order of presentations be set? Let's say if Joe must be third. Okay, well, in that particular case, so if we have, I'm going to copy this, bring it down. Now this will change because in the third spot we are fixing. So Joe is going to be on the third spot, which means that we no longer have, 6 people to try to order if Joe is going to be stuck at third. So that means that leaves us 5 people. So that means we're going to have 5 multiplied by 4. Okay, and then 3, 2, and 1. So really this is nothing else but simply 5 factorial. Okay, and this would have been 120 in terms of the number that we would have. So as soon as you fix somebody at a particular spot, that only leaves you and allows you to try to order the other spots. So that would have been the answer to part B. Now for part C, how many ways can the order of presentations be set if Joe is third, Jane is last? Okay, so in that case, so once again, if I take this, I'll duplicate it. So if Joe and then Jane, okay, so this is Joe and Jane, well, that now only leaves 4 other people to choose from. So 4, 3, then 2, and 1. So this would have been 4 factorial, right? So 4 factorial, so I guess that's 24. 4 times 3 is 12. 12 times 2 is 24. So that's the number of ways. So as soon as you start fixing some of the orders, it certainly does reduce, okay, what you have in there. Now the last one, part D, is probably the hardest. So how many ways can the order of presentations be set if Joe and Jane are together? Okay, so they must be together, which doesn't mean that they're together in a particular spot. They just must be side by side. Okay, so what we have is, in this case, so Joe and Jane are together. So this is, let's say, Joe, okay, and Jane. So they're fixed together. Now there are really 2 factorial ways to swap them, right? Because you can have Joe and Jane together, and then you can have Jane and Joe. All right, so from here, there's 2 factorial ways of swapping them, which is just 2. And now all the other individuals, basically we can order as you like. So what happens here is that if Joe and Jane are together, and we have, so if I take this once again and I duplicate it, and I put them as so, let's maybe change the color. Okay, so if we have that, and what that means is we have Joe and Jane, so they can be anywhere. So I'm going to just put, let's say Joe, Jane, so they can be like this. They're together. They certainly can be here. They can also be, right here, right? So they can be in the 2nd, 3rd spot, and so on. And you can arrange them anywhere you like, okay? But they're really just clumped together. Okay, and there's 2 ways because we can swap them. So this is interesting because now what we have is really they're just adding or they're acting as one unit. So whenever you are told that something is together, that they have to be clumped together, then what you want to find out is, okay, if they're clumped together, then how many different ways can I arrange them? Well, I can arrange them in 2 different ways when they're together. So Joe, Jane, Jane, Joe. If there are 3 things clumped in together, right, that would have been 3 factorial ways that you can arrange those 3. But then they're going to be stuck together. So they act as one particular unit, which means now, so we had 6 people, but 2 of those people are together. So we really have just 5 items in total, right? One of those items is that clump of togetherness, all right? So that means we have 5 factorial ways of now rearranging, okay, the 4 individuals that are alone, and then this clump that comes together. Plus that clump can be swapped, right? So it can be 2 factorial ways. So Joe, Jane, Jane, Joe. So this is going to be, so the answer is 2 factorial multiplied by 5 factorial, or simply just 2. Either Joe is first or Jane is first, and then multiplied by 5 factorial ways that you can rearrange now, okay, all of the different items. So this would have been, I guess, well, 5 factorial is 120 times 2, so that would have been 240 ways. So that's part D. All right, and that completes this particular example. So here's another example from this particular test. So in how many ways can the word quick be arranged so that Q and K are separated by at least 1 letter? Okay, so this is an interesting one. And students will run into some problems if you haven't seen this before. And how do we kind of think about this example? So we have, so quick has really 5 different types of letters, right? So Q, U, I, C, K. And you know that if you have 5 different letters, so the total number of arrangements, so the total number of arrangements would have been 5 factorial, which is 120. That is if, we didn't have any restrictions. Now we do have a restriction. So our restriction is that Q and K are separated by at least 1 letter. Now you can try, to pick your cases, right? And then see, okay, are they separated by 1, by 2, by 3, and so on and so on. And it would create a lot of cases for you, and it's actually quite a bit of a headache. So what you can do instead is kind of negate the problem and say that, okay, so in how many different ways can this word be arranged? Well, it can be arranged in 120 different ways in total, minus, so I can subtract, so I can negate the problem by saying, when are they together? Okay, because if I figure out how many times they are together, and I subtract it from the total, that's going to actually give me what I want. So this is kind of negating the problem in some sense. So let's do that. So here's my total number. And now I want to know, okay, so when are they together? So when are they together? Well, so that means you either have Q, okay, K, so that can happen, right? Or, you know, you can certainly have either K and Q. So here they're also together, so they're not separated by anything. Now, because we have two different letters, so really this is just 2 factorial, right? So 2 times 1. Different ways of rearranging, which is just the swapping. So that's 2 factorial ways, okay, how you can swap. So either Q, K, or K and Q. And now that also leaves me with another 3 different letters that I have. That would have been the U, the I, and the C. So in total, so this acts as 1 unit, all right? So we have 1 unit. This is going to be your Q, comma, K, and we can do that 2 factorial ways. And then you still have 1, 2, 3 other letters, which is the U, the I, and the C, which we can now start rearranging. So I have 1, 2, 3, 4 different units. So this is going to be 4 factorial ways that I can rearrange these. And then of course I'm going to multiply it by the 2 factorial because I can swap the Q and the K, okay, over. So 4 factorial, I guess, is 24 times 2, so that's going to be what, 48, right? And now if I take the total, which is 120, so 120 minus when they are together, which is 48, so that would have been, so 120 minus 40 is 80, and so I guess that's 72. So that is 72 different ways that they can be arranged such that there is at least 1 letter which separates this Q and K. So we've kind of used the opposite. Find how much the total, how much when they're together, and then just subtract them. And then that would have completed this particular example. Okay, so it's another one done. All right, so welcome back. So to another example of kind of ordering things up. So in this example, so you have how many arrangements can we make from the letters A, B, C, D, such that B is never beside C or D. Okay, so this is not an easy one. And I'm going to do it kind of 2 different ways. Because we only have A, B, C, D, which is really just 4 letters, I can use the brute force way. Now, the reason why I'm going to do the brute force way is because then I'll try to give you an intuition of how to think about the problem, all right? So that you can extrapolate it to harder problems. Okay? And then I'll make another actually video exactly kind of the same, but it's going to be more. Okay, it's going to be bigger so that we can't use brute force anymore. So we have to have some kind of an intuition. Okay, so let's try this. So what this says is we want to know how many arrangements. There actually won't be too many because we have just 4 letters, where B is never beside C or D. So they can never be beside each other. Okay? So now let's try this. So in how many different ways can I rearrange all of them? Okay, so I'm going to kind of take it and rewrite in brute force ways. I'll do it kind of in fast forward fashion, but I'll just do all the arrangements possible. Okay, let's do that first. All right, so it took a little bit because we have to go through all the different arrangements we can have. So we know that this really would have been 4 factorial ways, right? So we have 4 factorial ways, which is 24 ways that we could arrange these letters, and here they are. So if you put A first, you know, B first, C first, D, okay, so it's 6 each, so 6 times 4 is the 24. So that's the total 4. Now, what they're telling us that B, okay, right here, is never beside C or D. Okay, so what I'm going to do, and I'll switch the color just so that we can see it. So we're going to first, you know, find out, so when is B, okay, actually beside C? All right, so this can happen either BC, okay, or, you know, 2 factorial ways, or CB. All right, so this is, you know, 2 factorial ways, or just 2 ways. Now we can just swap these, okay? And that's going to now leave us, so if we have them together, right, then that leaves, I guess, the, you know, the A and the D to float around as it likes. So we have basically 3 units. We have the B and the C, okay? And then we're going to have the A and the D. And this, you know, in total can be 3 factorial ways rearranged. And then multiplied by that 2. So it's going to be 2 factorial times 3 factorial. So this is going to be 6 times 2, which is equal to 12. So there are 12 total arrangements where B and C are actually together. So let's find them. Okay, when is B and C together? So I'm going to put a check mark. So B and C is here. It's not in the second one. Okay, here it is again. So C and B, so either one or the other. It's not in that one. B and C, so here again. C and B, here again. So that's 4. All right, so now B and C, that's right here. B and C right here. None there. Okay, so B and C, so right, that's right here, right here. That is it. Okay, and now again, so B and C. Okay, C and B, B and C. Okay, and that. So that's a brute force way, right? And now in total we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so it's exactly what we would have counted by just using our intuition. Okay, and how many different ways can I rearrange these? So that's 12 total ways. Now, it also says that B can never be beside D. Okay, so I'm going to switch the color just so that, again, we can see it. So B can never be beside D. So this can happen like this. So either BD or DB, which just comes, again, because there's only 2 letters. So 2 factorial, or 2 ways. And once again, you know, how many ways can I rearrange this? So if I group this as 1 unit, and then we'll have A and C right here. So these are 3 units, so 3 factorial ways. So again, so, you know, 2 factorial times 3 factorial. So in total, you know, 12 ways that we would have this. Okay, now let's find them. So that was B and D together. Okay, so I'm going to do it beside. So when are B and D together? So they're right here. B and D right here. B and D, so right here. Okay, right here. So that's 4 ways, B and D. And, okay, B and D here and here. Okay, so that's right here, B and D, that's right here, and right here. And finally, the last one, B and D, okay, right here. Okay, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so that's exactly what we wanted. Now, the reason why I wanted to show you this brute force, because oftentimes when students do this, the approach is, and it's a correct approach. So what you would do is you would find, okay, what is the total number of arrangements? Well, in our case, it's 24. And then you would want to subtract. So you would want to subtract, so minus, when are, B and C together? So we found, so that was 12 ways, right? And then minus again, when are B and D together? But that's also 12 ways. So if you notice, you'll get 24 minus 12 minus 12, which is going to be 0. So what has gone wrong? Well, what has gone wrong is, because if you notice here, you're actually counting certain things 2 times, right? So here, B and C, or C and B are together, and B and D are together. So you've counted them twice, right? And that happens, now that's why I used kind of 2 colors and the 2 check marks, because we can go along within here and then see that, okay, how many times have I counted them up? Okay, again, so that would have been 1, 2, 3, 4. 4 ways that I've double counted. So if you're going to be using this method, which is a good method, I use this method. So the total minus when they're together, okay, there is an overlap. Okay, so it's almost like, you have, and this will come back to you when you start studying Venn diagrams, because you have an overlap between, so B and C and then B and D, and they do overlap, which means that you're actually going to be counting them twice sometimes. So in that case, we actually, when we say total minus when B and C are together, minus when B and D together, we have to now say plus, because we have to add back what we subtracted 2 times, right? So now plus, okay, these particular cases. So this would have been, 1, 2, 3, 4. Okay, so when that happens, okay, so plus, okay, whatever I counted twice. And that would have been 4. But now, how do we come up with this 4 in terms of an intuitive amount? So what do we have to think about? Well, we have to think about, okay, the cases when we have, notice in all of them, okay, the B, so when we have the B in the middle, and then, you either have a, C here and a D here, or you're going to have B in the middle and then a D, okay, and a C. Because in these two cases, okay, B is going to be beside C and it's going to be beside D in both ways. And now that, of course, so this now acts as 1 unit, okay? So this acts as 1 unit. We have 2 different ways of arranging, of having this around with B in the middle. Okay, so the only ones that can swap are the C and the D. The B can't swap with any of them because then it's not going to be counted twice. So when that B is in the middle, so this happens 2 factorial ways, right? And then, okay, you still have that A, which can be, so either in the back, okay, or it's going to be in the front. So there's two units, 1 and the A. Okay, so that is 2 factorial ways. So this is going to be times 2 factorial, or 2 times 2, which is just 4. And that's where this 4 comes from. So we have to add that back because we subtracted it 2 times. And oftentimes, sometimes even in the solutions in textbooks, they forget about this, that they actually have subtracted it 2 times. So in total, if we had this, if we did this entire thing, the answer is actually 4. There are only 4 ways, so coming back to the original question, that you can arrange the A, B, C, and D such that B is never beside C or D. Okay? Now it's a difference, if they say B never beside C and D, okay? But when they say or, we have to go through this entire process. And yes, that's indeed. So if we go in here, by brute force, was there really 4 ways? Well, indeed, so here's 1, here was 2, okay, so that was just 2 ways here. I guess this is 3, and then this is 4, and that is true. Those are the only arrangements. right, that we had. And that was my answer. So this is a very long solution, but I wanted to give this so that you can actually get a nice and decent example, okay, out of this. And then I'll do kind of one more, which is not going to be just 4, it's going to be much bigger. Okay, that's it for this question. All right, so here's another example in terms of counting. So ordered counting. So we have a rectangular table and it sits 10 people. It says that Grace will sit at the head of the table. And now if BJ can never sit beside Tommy or Jill, then in how many ways can the sitting arrangements be made? So this is a hard question to be able to do. Now there is, I guess, a way of interpreting this. So, you know, I'll make one particular interpretation, okay, to give you some kind of a sense of how to approach this. Okay, so it says, so Grace will be sitting at the head of the table. So there's 10 people. So I'm going to, so here's a rectangular table, okay? Now, the head of the table, so Grace, you know, you can just assume that, let's say maybe this is the head of the table. Although sometimes, you know, people can say, well, I guess it could be either here or it can be here, right? So we're going to just assume that, you know, head of the table is kind of at the top here. So that's the head of the table. Now, the rest of the question, so if BJ can never sit beside Tommy or Jill. So Grace is fixed. All right, so Grace is fixed at the head of the table. Now I can rearrange 9 people. All right, so there's now 9 remaining people that I would have. So I guess it would be kind of 1, 2, 3, 4, 1, 2, 3, 4, and I guess we can sit another one here. Okay, so that's 9 people that I can rearrange. So the total number that I can rearrange is 9 factorial, right? So there's 9 factorial ways of being able to rearrange this. That would have been easy if we didn't have this kind of constraint that BJ can never sit beside Tommy or Jill. So what I'm going to do now is I'm going to say, okay, so that's the total minus. Now, when is BJ, okay, sitting beside Tommy? Okay, so when are they sitting beside each other? Now, I can arrange them, right? It's either can be, BJ Tommy or Tommy BJ. Okay, so this is just 2 factorial ways of changing them around. And now that will leave me, okay, so I guess if I would fix that, so that would leave me 1, 2, 3, 4, 5, 6, 7 different ways that I can order the rest. Okay, so I have 1 unit, so that is my BJ and Tommy, and then I still have 1, 2, 3, 4, 5, 6, 7 around the table, right? Around the table, and now I can kind of swap them where BT is just 1 unit. So that means this is going to be, I guess, 8 factorial, right? So 1, 2, 3, 4, 5, 6, 7, 8. So I can rearrange these in 8 factorial ways when B and T are together, multiplied by, 2 factorial, or just 2, because I can rearrange BJ and Tommy, either BJ Tommy or Tommy BJ. So that is the total, okay, when BJ and Tommy are together. Now, I don't want them together, so I'm going to be subtracting it. And now the other one, it says that BJ can never sit beside Jill either. So notice this is or, so Tommy or Jill. So that's going to be the same thing. So I will do the same thing, so it's say subtracting. So now BJ and Jill, so when they're together, so that's identical to 2 factorial, right? And then we would have exactly this, except with BJ and Jill, so that would have been 8 factorial. So 8 factorial ways multiplied by 2 factorial that I can swap these two. Okay, so that is now subtracting that. But it now brings something into light. And if you do this, you have the right approach, but you have actually counted something twice. So notice that what could happen in this seating arrangement, okay, so if you would be putting these in, so let's say, I would do something like this, okay, let's say BJ was here, okay, Tommy, let's say, was here, and then Jill was here. So we have clearly, so BJ and Tommy, so that is getting counted here, right, and subtracted. But BJ and Jill, so this right here, is also being counted right here and subtracted. So we've counted, or we subtracted them 2 times. So we've over subtracted. Okay, so we have to be careful there. So that means that, we shouldn't subtract them 2 times. We should just subtract them once. So we should actually add at the end. So addition. So this is going to be adding when BJ is kind of in the middle, right? Fixed. And then you have Tommy and Jill on the sides, right? And it can be either, Tommy, BJ, Jill, or Jill, BJ, Tommy, right? Because the Tommy and the Jill can swap together, and that is, so 2 factorial ways to swap them together. And now this acts as 1 unit, right? So if this acts now as 1 unit, so what we have is, we have this big unit, so that's that. And then what else? What does that leave me? Well, that leaves me, so in terms of the number of seats still, that's 1, 2, 3, 4, 5, and 6. Okay, so that's 6 extra ones that I have. 1, 2, 3, 4, 5, 6. And now I'm going to be rearranging all of this. So I have 1 big unit, 2, 3, 4, 5, 6, 7. So it's going to be 7 factorial ways of rearranging those. And then when these guys were together, so that would have been that. And we have to add it, because what we don't want happening is we don't want to be subtracting it 2 times. So this is a rather, kind of lengthy example where you have 9 factorial ways minus, right? Now it's going to be BJ and Tommy, so it's going to be 2 factorial times 8 factorial minus BJ and Jill. But then we have to be careful, and we have to add this right here. And that's actually the setup. And if I'm going to leave the calculation to you. You can plug in those numbers and find out what the answer is. But very often this is forgotten. Okay, this. And the reason, again, we're doing that because of the fact that we have actually subtracted it 2 times here, when BJ is kind of stuck in the middle between Jill and Tommy. So we have to be careful with that. Okay, so that's another really nice example for this organized counting. Hi, all right, so we have, here's a really nice example of trying to count the number of arrangements that we would have from a particular word. And the only problem is that the word is classroom, and it has S, which is appearing 2 times, and then we have the double O, which appears 2 times. And if we wanted to be able to count it, right, in terms of the arrangements, we can't just simply say, well, classroom, in this case, has 9 letters, so the way to rearrange them is 9 factorial ways, which would be true. The only problem is that the S's are not distinguishable, right? So it's not like, if we would label them, let's say we had S1 and S2, and then O1 and O2, then it would differentiate between them. And again, that case, we would have 9 factorial ways of being able to arrange them. But this comes into effect when things are actually repeating. So I'm going to use the kind of the repetition with regards to multiple letters or multiple objects that are kind of repeated within. And I can put up a link up above there. I did a video okay, with a little bit smaller item and example, so you can watch that before here, because I present on what I actually use. Okay, so for part A, in how many different orders can the word be arranged? Well, so as I already said, so we have now, so we have C, L, A, S, S, R, O, O, and M. So that would have been 1, 2, 3, 4, 5, 6, 7, 8, 9 letters. 9 letters I know I can rearrange 9 factorial ways, but because of the fact that S is repeating 2 times, then what we do is, okay, so this is 2 factorial, so that we remove the ones that, you know, if let's say S is first, S is last, it doesn't really matter. We don't want to count them 2 times. And then the same thing here. So the O's are appearing 2 times. So we would have been dividing by 2 factorial once again. So this would have been just 9 factorial divided by, I guess, by 4. Okay, so we can do that. So 9 factorial divided by, well, 2 times 2, so that's 4. So that's still quite a lot of ways. So 90,720. Okay, so that's the first one. Now, B is much harder. So this would have been A. Okay, now in B, how many different 4-letter arrangements can be made from classroom? That's difficult, actually, to do. Now, if we would have that we had no repeating, right? So if S wasn't repeated, if they were actually distinguishable in some particular way. So if I would take this, let me duplicate it here. We'll bring it down. And we would say this is S1, S2. Okay, this is O1, O2. So that would distinguish between my letters. Then if I wanted to make 4-letter words, we know that we can use, so this would have been 9, okay, P4. So basically, how many permutations can we have, okay, from 9 letters that would be distinct letters? Then this would have been the answer, right? But now, unfortunately, we can't really do that because of the fact that the S's are not distinguishable. We don't know which one is 1, which one is 2. So how would we actually approach this? We had a very nice way of doing it when we chose all the letters, right? We would just divide by how many times the S's are repeating in terms of factorial ways, so 2 factorial. But we certainly cannot do this. Okay, so we can't say this is 2 factorial, and then, you know, we're done. This is actually not true, wrong. Okay, and in general, this will be wrong. Doesn't mean it's always wrong, but in general, this is wrong. And I did an example of this as well, okay, in that video that I was linking for you. So if this is incorrect, then we have to do, you know, certain cases. So we know we're going to be picking 4-letter words. So 4 letters. So what I'm going to do is I'm going to kind of break this down into cases. So here's case number 1. Okay, and this is what I would encourage you to do. For your case number 1, always try to pick, let's take all the letters, okay, but not repeat them, right? And then say, okay, if I did this, so now I actually have only 7 letters in total. You know, and how many different ways could I rearrange them? For this, indeed, it's 7P4, right? So how many permutations are there? So that is true if I would take that. So that's the case when there are no repetitions at all. Okay. Now, case number 2. So now I'm going to start picking off all the cases, and let's say, okay, they are repeating. So let's imagine, okay, so in terms of the next item, okay, that I'll do, is what if both of them repeated? So I had an O and an O, and I guess an S and an S. Well, if I'm choosing 4-letter words, okay, so in this particular case, right? And I only dealt with these, so in how many different ways can these be rearranged? Well, this is fair game. So I can literally say I have 4 total letters, okay? And then this would have been 2 factorial divided by 2 factorial. So I can use exactly what I did in part A, except just with 4 letters, 1, 2, 3, 4. And this would give me the total amount. So now that's case 1, and now case 2, and both of them have actually repeated. Because I can't have any more letters, right? There's only 4 letters in total. So that's 4 factorial, would have been 24, divided by 4, so it's 6 different ways that I can rearrange these. Okay? So that's what I would have had here. Now, what other cases can I have? So case number 3, and this is kind of what you would have to go through is, okay, so in the next one, okay, is what if I was repeating only the O's? Okay? What if I only repeated only the O's? And now the rest, okay, of the letters that I would have, okay, what else is remaining? So that means all the other letters could only happen once. So in that case, so that would have been the C, the L, the A, okay, the S, the R, and the M. Okay, so I can pick 2 letters, so any 2 letters that I want, okay, and then bring them in here. So now notice, so what I would have is I would have 1, 2, and some 2 other letters. So what would that be? Well, so that is 4 factorial divided by just 2 factorial because the O's are repeating, right? That's with any 2 of those letters. But of course, I could pick, CL, I could pick CA, right? I can pick CS, okay, to be those 2 letters. So, how many different choices would I be able to pick out of here? Now, if you would do all of that, so if you did CL, CA, really, so what you're having is you have 1, 2, 3, 4, 5, 6 different letters, and you're only choosing 2 of them that you like, right? Now, the order here doesn't matter because if you say CL or LC, they're still the same letters, and then they're being rearranged there. So I have CL, CA, CS, okay, and of course I would have CR and CM, okay, so I would do that. So that's kind of takes all the C's in, and then I would do the same thing. So I can have, LA, then it would have been LS, it would have been LR, would have been LM, okay, so that's all the different ones for that, and then I can do the same thing. So it would have been AS, right, AR, AM, okay, and then finally, you would have SR, SM, okay, so those are the only ones, and then RM. So in total, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And when you study finally, when you have kind of combinations, right? And when you get there, then this, okay, this is just a hint for you. I did it by brute force, but this would have been 6, choose 2, which indeed is 15. But you get to that when you study actually combinations, okay? And maybe you haven't yet, so I just did it by brute force. So there's 15 different ways, okay, that I could do this. So that's case number 3. Okay, so that's 15 different ways of choosing those 2 letters and then multiplied by how many times I can rearrange the O's with those 2 letters. So that's would have been that. So that's 15, I guess 4 factorial, so that's 24 divided by 2 factorial, so that's 15 times 12. Okay, so we would have that. Now, the last case, so case number 4, is the same thing, except now you've repeated the S's, right? Okay, and now you pick, okay, the same, so the same letters. Instead of the S, there's an O, but this is the same exact thing. So 15, 4 factorial over 2 factorial to get that out. And now you have all the different cases, because there's no other cases. The only other case that is remaining, okay, is, you know, when nothing is repeating, but we just did that as case number 1. So now you have to add this plus when they both repeat, when only one repeats, the O repeats, and when only the S repeats. And when you add them all up, you get your answer. All right, I'll leave that for you, because I think the idea was, what was the intuition behind trying to break this problem down? So this is a great problem of finding, and you do have to break down the cases, unfortunately. Okay, thanks for watching this one. So another example done. Welcome to this example. So we have this weird figure here, and this example actually ties in Pascal's triangle. So what you learn in Pascal's triangle in kind of ordered counting. I'll put up a link up above there to Pascal's triangle and some kind of thought process behind it. So I think it's very useful because it is used in the application of counting the number of paths. It uses kind of the same concept. So, you know, when you're doing paths, you can either have, sometimes you'll have like a checkerboard, and you want to see when the checker is going to get to a certain point and how many different ways can it get there. Or, you know, you have kind of communication links between maybe cities. And then, you know, you have all of these communication links between cities, and you want to know, okay, well, how many paths are there from one city to another in terms of the communication? So this is exactly it. Instead of cities, we have letters, but you can think of, you know, A being a city, B being a city, C and D and so on. And these cities are connected by lines or communication links in some way. They're asking us in this question to go from A all the way to K and find out, okay, how many total paths are there to get from one point to another? So let's do that. So I am going to use the concept of Pascal's triangle in order to do this. So I'm going to be starting from right here, and I want to be ending up all the way over here. Now you can draw the paths one by one, and it would get annoying and extremely complicated in terms of you know, overwhelming maybe in terms of looking at the whole thing. So instead, what we will do is we're going to just create the paths from each city to the next. So for instance, to get from A to B, there's only one way to do it. Okay, so I'm going to put a little 1 there to go in this direction. Now, to go to C, okay, you will notice that there's only one way from B to get to C. Now, we're assuming we can't just keep going back between cities, right? Once we traversed something, you know, we're not going to be traversing it again, going back and forth, back and forth. So we're kind of, you know, doing the paths which have the least amount, all right, okay, of the direction. So to get to C, there's only one way to get there from B, okay? So we're just going to be looking at this, okay, and then doing that answer right here. So now to get from B to D, there's also only one particular way. But now something interesting happens, because you will notice that I can actually go. So I'm going to kind of change the color here. Notice that I can go from C to D, okay, in this direction, right? Now we know that to get to C there was one way, okay? And now to get to D, so to get to D right here, if it was from B, there was only one way to do it directly. But now, okay, if we consider both from C and from B, then we would say, okay, that's 1 plus the 1. So this is actually 2 different ways to get to D. And the 2 different ways would have been the AB, okay, to D, and the ABC to D. So those would have been the 2 different paths there. All right. So from C, okay, and then from B, we can get to D. Now you can do that also in the other direction in terms of getting to C. So I can get to C right here, going in this direction from D. So I can get to C from B and from D. And that would have been, so now notice, okay, that going in this. Now I can't traverse back So I'm not going to be using this 2 right here because I don't want to go back. So I'm going to be using the green. So that's the 1 plus the 1. So this would have been 2 ways to get to C. All right. And that's something you're going to have to think about a little bit. Okay. Now I'm going to go back. Okay. And now we continue. So now to get to E, so I can get to E from C and from D. And notice there's 2 ways to get to C and then 2 ways to get to D if I count all the paths. So that's 2 plus the 2. So that means 4 total ways to get to E. And now to get to F, okay, so that there's only 1 way. Okay, so that would have been just 4. Okay, that's in this direction. And then that's going in this direction. So that's from E to G. So this is also 4, right? Because it's for this, but it's also going through F. So I have to add up the 2 nodes there. So I'm going to be adding this and this. So now this is going to give me 8. And now I can continue. So now there's only 1 way to get to 8. To get to H. And now be 8 different ways because I'm just looking at the previous node. And now again, so now I'm going to be running into problems. Okay, so right here, notice that what I have is to get to J, so there will be 8 different ways, right, from H. To get to I, there's 8 different ways. To get from H to K, okay, there's 8 different ways, right? However, okay, now notice that you can also get to K from here. So that would have been 8, okay, going from J, 8, okay, going from H, and then 8 going from I. So in total, so that's 8 plus 8 plus 8, which is 24 different ways that we would have there, okay? So that's an interesting example to be able to use Pascal's triangle in order to actually count the number of paths. And I would encourage you, to kind of erase this and then do it on your own. And in particular, understand what has happened around here. Okay. And then also understand what has happened around here to get to K. All right. Okay. So that was another nice example of Pascal's triangle application. Okay. So that completes the entire test. I think it's a good one in order to get you started on organized counting. I specifically put a lot of examples that are a little bit more challenging than the basic ones, which you probably will get in your courses of data management and probability. These ones will certainly challenge you in some way, and if you can do them and understand them, amazing. Okay, thanks for watching. See you in future videos. Bye, everybody.